Hello everyone, we are going to discuss about the Ampere circuital law. So according to it, the closed line integration of magnetic field is equal to mu naught times the total current enclosed by the system. So for applicability of the Ampere circuital law, we must have a closed path. So the path must be closed. For open path, this law is not valid. Let's try to find a magnetic field due to a infinitely long wire carrying current. Using Ampere circuital law. So this is an infinitely long wire carrying current. So this is XY beta wire is carrying current I. Suppose we are considering if we have to find the magnetic field at any point P at a distance R from the wire. The point is at a distance R. So to find the magnetic field at point P, we have to consider a closed path. We are considering a closed circular path basically. So this path is a circular path. And as the distance from the wire to the point P is R, so the radius of the circular path is also R. So as we have the Ampere circuital law, that is line integration B dot dl is equal to mu naught I till current enclosed. So the current flowing through the loop is I, so mu naught I is till current enclosed by the loop. So just if we integrate it, if B is constant, so and we can write the integration of the closed integration dl equal to mu naught I. So that's B twice pi r. So the closed integration of dl is nothing but the circumference of the circle. So twice pi r is equal to mu naught I. Thus B is equal to mu naught I divided by twice pi r. So this is the same expression that we have already derived using the Biot-Savart law. So coming to the next topic, the next application of the Ampere circuital law, we are going to determine the magnetic field due to a solenoid. So here we can see a solenoid. A solenoid is nothing but a helical spring, that is a wire has been wound up in a helical shape. So for this we are considering the current I is flowing through this solenoid. If let we consider that current I is flowing through it, and there is a total n number of turns. So total number of turns is equal to n, and total length is equal to n by total length is equal to L. So number of turns per unit length is equal to small n L and say capital N by L. So determine the magnetic field. We are considering a closed loop like this. Suppose this is A, B, C and D. So as per the Ampere circuital law, we can write the closed line integration B dot dl is equal to mu naught times of I enclose. So here we can say we can write actually we can break this closed line integration in 4 segments from A to B. B dot dl plus B to C B dot dl plus C to D B dot dl plus D to A B dot dl is equal to mu naught of the current. As we know the basics of the Fleming's law, the magnetic field is perpendicular the plane of the any loop of the solenoid. So magnetic direction, the magnetic field is along this direction. So as a dl for BC and AB is perpendicular to that the magnetic field. So these two terms BC and AD, these two terms will be finished because their dot product will be 0. So the remaining term of the equation we can just simplify as A to B B dot dl plus C to D B dot dl is equal to mu naught times of total current enclosed. So again, if we see the arm AB is lying outside the magnetic field, so there the magnetic field component is 0 itself. So this component of the integration is also 0. So our final, this component is also 0. So our final result, after simplification, we will get like this. So B dot dl is equal to mu naught of the total current enclosed. So this is nothing but B to the length of the arm BC, say it's L, is a mu naught total current enclosed. So if there are n number of turns, if there are n dash number of turns from B and C dash, so B and C dash there are n number of turns, so we can write total number of turns multiplied total current. So actually I enclose is nothing but number of times of the turns multiplied by current flowing through each turn. So we can write I enclose equal to I into N. So B equal to mu naught N by L into I. So as we have already considered the number of turns per unit length is equal to small n, so you can write mu naught N I as small n is equal to N by L. So this is our final expression for magnetic field due to a solenoid. Magnetic field due to a solenoid. We are We'll do the next example of application of the Ampere circuital law, and we will find a magnetic field due to a toroid. So this is nothing but a circular loop are arranged in this fashion. So let current I is flowing through the loop. Let total n number of turns. Total number of turns be n number of turns, and I be the current flowing through each turn. Current flowing through each and every turn. So for this, we are just considering a circular loop. A circular loop. A circular loop to evaluate the Ampere's circuital law. So this is the loop we are considering, is a closed loop we are considering. So we already know the Ampere circuital law is nothing but the closed integration B dot dl is equal to mu naught times of the total current enclosed. So for this loop, let the radius of the toroid is r. So this is r. Radius of the toroid is r. So the integration, if we do the integration, we will get mu naught twice pi r is equal to mu naught times of total current enclosed. So we can write the integration like this, because the magnetic field produced by the toroid at its point is perpendicular to the dl vector. So we can write the integration of b dot dl as b twice pi r. Again, as we know that total current enclosed is nothing but the total number of turns multiplied by total current in each turn. So we can write total number of turns by total current in each turn. That is, I enclosed is equal to n times of the I. So B can be written as mu naught total number of turns, total current flowing through each turn, divided by twice pi r. So this is the expression of the magnetic field for a toroid. So thank you everyone. Thank you for listening.